In this video, we're going to look at reaction mechanisms, which is some speculation kind of, it's sort of hypotheses about how reactions actually happen, because they don't always happen the way we write them, and evidence is pretty clear about that in some cases. So let's just do a little review of collision theory. So remember that particles that are in effective collisions have to have two factors that are right. One of them is the orientation. They have to be oriented in the right way so that the atoms that end up being bonded in the product have an opportunity to collide with each other. And then the other thing is that they have to have enough kinetic energy to allow there to be sufficient orbital overlap that new bonds can form between the atoms that are going to end up being bonded in the product species. So the rate of reaction then by collision theory is proportional to the number of effective collisions that occur in any unit of time. So one of the important things that we need to understand how reaction mechanisms work is the idea of an elementary process. So an elementary process is a reaction that occurs exactly as it is written in one step. And for elementary processes, you can use some common sense to predict how the rate of reaction will be dependent on concentration. In other words, what the order should be. So here's the simplest example. Reactant A decomposes into products. In this case, if we have more A, there is more A to decompose, and so we should get more products. So the rate is going to be proportional to the amount of A that we have in a given space. So the rate law, it's first order. Say we have two reactants, A and B, forming products. Well, if we have more A, then that should mean we have more A to react. If we have more B, then that means we have more B to react with A. And having more A means there's more A to react with B. So increasing the concentration of A should provide more A to react. Increasing the concentration of B should provide more B to react. So this is first order in both of these reactants. Let's look at this one. Here it's 2A decomposing into products. So here an A has to collide with an A. So if we think about this, we could also write this as A plus A makes products. So having more A gives more A to react, but having more A also gives more A to react with. So just like the second reaction depended on A and B, this one is going to depend on A and A in a sense. So this is going to be second order in A. If we have 2A plus B making products, then having more A will give more A to react, and it will also give more A to react with both the other A and the B. And so this is going to be second order in A, but only first order in B, because adding more B only gives more B for the A's to react with. So the rate law here is going to show a second order in A and a first order in B. So for an elementary process, to kind of summarize this, the order in any reactant is the same as its coefficient in the elementary process. Now remember, this is only for processes that happen in a single step, and many reactions don't actually do that. So for those kinds of reactions, it's helpful to come up with a series of steps, which are elementary processes themselves, that explain how the reaction actually occurs. For example, in this top reaction, O3 reacting with 2NO2 to make N2O5 and O2, the rate law is rate equals K times O3 concentration times NO2 concentration. So it's first order in O3, which matches its coefficient, but it's also first order in NO2, and that doesn't match its coefficient. So we know, because this is a fact, this is experimentally determined, that means this cannot be an elementary process. It's not possible, because the order in NO2 would have to be 2. Now for the second reaction, the order on NO is 2 and the order on Br2 is 1, and that does match the coefficient, so that means this could be an elementary process. It doesn't mean that it is, but it could be an elementary process because it does match the coefficients. However, it does require 3 particles to all collide with one another with a proper orientation at the same time. 2 NOs and a Br2 have to all be oriented exactly the right way. And that's maybe unlikely to occur, at a high rate. So if the reaction rate is actually pretty fast for this reaction, it seems like there probably would be a different mechanism by which the reaction occurs. So what a mechanism is a series of elementary processes, and this is something that you can propose and you can seek evidence that supports it, for sure. And it is based on evidence. It's based on how the experimental rate law dictates that the reaction occurs. But you never actually can prove it. It's just sort of a possible helpful explanation. One thing that has to be true is that you have to be able to add the steps up, and it has to sum up to the overall reaction. And the coefficients don't always have to, quantitatively add up right. But the reactants and products of the sum of the steps should be the reactants and products in the overall reaction. And then the rate law that's given by the mechanism, by whichever step in the reaction determines the rate law, it has to match the experimental rate law. Okay, so for this O3 plus 2NO2 reaction that we saw before, we know that it's first order in O3 and it's first order in NO2. So here's a proposed mechanism. So remember, these are both elementary processes, step 1 and step 2, in which we could produce this possible outcome. So to answer the question, could this be a mechanism, the first thing we want to do is make sure that the steps add up to the overall reaction. And if we add these together, we will have O3 plus NO3 plus 2 NO2s makes NO3 plus O2 plus N2O5. And we have NO3 on both sides, and we can cancel it out. And when we do that, we notice that we have exactly the same reaction as the overall reaction that we were first looking at. Okay, so that check works out. The second thing is, does the slow step, which will determine the rate, have a rate law that matches the overall rate law? And in fact, it does, because it's first order in O3 and first order in NO2, and the coefficients on O3 and NO2 are both 1s. So this could be a mechanism, because the two steps add up to the overall reaction, and the rate law for the slow step, which remember is an elementary process and we can predict it, does match the overall experimental rate law that we know is true because it's determined by experiment. As we examine this mechanism, we see the thing that canceled out there. This is an example of what we call an intermediate. An intermediate is produced in one step of a mechanism, and then it's consumed in a later step in the mechanism. So it's not in the overall reaction because it ends up canceling out. In that previous reaction, the mechanism that we proposed had the first step in the mechanism be the slow step. When the first step is fast, then it does not determine the reaction rate. When that's the case, we have to use something called the steady state approximation. And this is the simplest example of using the steady state approximation. And it's also the one that you're most likely to encounter on, say, the AP test if they're going to ask you to evaluate a mechanism. Let's switch to a different space that has more room to be able to work this out. So if this is a mechanism, then those two steps have to add up to make the overall reaction. Let's see if they do. We would have NO plus Br2 plus another NO, and the NOBr2 looks like an intermediate, so that's going to cancel out. And on the right hand side, that just leaves us with 2 NOBr. Okay, so, and the phases check out, so that check works out. So this could be a mechanism from that standpoint. Now, we're going to find out if the rate law matches the experimental rate law. So the rate law is going to be based on the slow step, which is going to have this rate law, rate equals K times concentration of NOBr2 to the 1 power times concentration of NO. The problem is we can't say yes or no if this matches the experimental rate law, because the overall experimental rate law has Br2 in it and does not have NOBr2 in it. So we're going to do a little bit of a trick here. We notice that the fast step, the first step, is in dynamic equilibrium. That means it's going forward and backwards, but it's going forward and backwards at the same rate. That's what the double-headed arrow that we see here means. So we're going to take advantage of that. The rate law for the forward reaction is going to be rate, let's say rate forward, is equal to K1 for first step, forward for the forward reaction of the first step, times concentration of NO times concentration of Br2. The reverse reaction is going to have this rate law. Rate reverse is K1 reverse, so this is the rate law for the reverse reaction, times concentration of NOBr2 to the 1 power. Because this step is going forward and backwards at the same rate, the forward rate equals the backwards rate, which means K1 forward times concentration of NO to the 1 power times concentration of Br2 to the 1 power equals K1 reverse times concentration of NOBr2. And what we really want to do is get rid of concentration of NOBr2 in our rate law for the second step. So let's solve for it. If we divide both sides by K1 reverse, we get K1 forward divided by K1 reverse times concentration of NO times concentration of Br2 is equal to concentration of NOBr2. Now let's substitute back into the rate law for the slow step, which said that rate is equal to K times concentration of NOBr2, but we now know that we can substitute for that K1 forward divided by K1 reverse times concentration of NO times concentration of Br2, and then that was multiplied by concentration of NO. But K1 forward divided by K1 reverse times K, that's just another constant, so let's just rewrite that as K primed, and then times concentration of NO times concentration of Br2 times concentration of NO again, or K prime times concentration of NO squared times concentration of Br2, and that matched the experimental rate law. And so both of the checks that we need to happen, one, that they add up to the overall reaction, and two, that the rate law for the slow step matches the experimental rate law, both of those things check out. So it is a possible mechanism. So next we're going to look at a more complicated application of the steady state approximation. So to do that, let's just remind ourselves what the steady state approximation is. The idea of the steady state approximation is once the reaction in its mechanism has established a steady state of reaction, the concentration of any intermediate stays about the same. In other words, any intermediates being produced in a step is being consumed at about the same rate that it's being produced. And so its concentration is relatively constant. So now we're going to evaluate this reaction with this three-step mechanism, and nobody's telling us what the slow step is. So there's a way to deal with that using the steady state approximation. Again, we're going to go to a space that gives us a little bit more room to write and try to solve this problem. So it's proposed that this could possibly be a mechanism that explains the reaction that's given. So the first thing we have to do is make sure that the steps add up to give the overall reaction. We've got two intermediates, NO3 is 1, and NO is 1. So with those canceled out, we'll get N2O5 plus making NO2 and O2. And some of the NO2 is going to cancel out on both sides to give the overall reaction. So even though the stoichiometry, the numbers don't come right out to the overall reaction, it doesn't have to quantitatively all add up. Okay, let's tackle the first intermediate, which is NO3. The steady state approximation says once this reaction gets going, the change in concentration of NO3 with respect to time is going to approximately be 0. In other words, its concentration is not really changing because it's being produced at the same rate it's being used up. So we're going to write an equation based on that idea. How does it get produced? Well, it gets produced in the first step, in the forward version of the first step. So K1 forward times the concentration of N2O5 is the rate of production of NO3. How does it get consumed? Well, it gets consumed in the first step in the reverse reaction. So consumption and production are equal, so we're going to set an equal sign here. So K1 reverse times concentration of NO2 times concentration of NO3. It also gets consumed in the second step. So that's K2 times concentration of NO3 times concentration of NO2. And it gets consumed in the third step. So plus K3 times concentration of NO3 times concentration of NO. So this is the equation that basically says the rate of formation of NO3 is equal to the rate of consumption of NO3. Let's simplify this a bit. We can pull out of the right-hand side concentration of NO3 because it's in all three terms. So that times K1 reverse times concentration of NO2 plus K2 times concentration of NO2 plus K3 times concentration of NO is a bit of a simplification. Now let's solve for concentration of NO3 because it's an intermediate and we may have to substitute later. So concentration of NO3 is equal to K1 forward times concentration of N2O5 divided by K1 reverse times concentration of NO2 plus K2 times concentration of NO2 plus K3 times concentration of NO. Our other intermediate is NO. And we know then that concentration of NO is unchanging. So the rate of change of concentration of NO is about 0. Well, NO is formed in the second step. So K2 times concentration of NO3 times concentration of NO2, that's the rate law for the second step, equals to the rate of consumption of NO. But NO is consumed in the third step, so that's K3 times NO3 concentration times NO concentration. Let's solve for concentration of NO. So concentration of NO is equal to K2 divided by K3 times concentration of NO3 times concentration of NO2 divided by concentration of NO3, which just works out to K2 over K3 times concentration of NO2. So now that we know what concentration of NO is, let's substitute this for concentration of NO in this equation. So concentration of NO3 can now be thought of as K1 forward times concentration of N2O5 divided by K1 reverse times concentration of NO2 plus K2 times concentration of NO2 plus K3 times concentration of NO. But that is now going to be replaced with K2 over K3 times concentration of NO2. And we can pull NO2 concentration out of the denominator. So this is now equal to K1 forward times concentration of N2O5 divided by concentration of NO2 times K1 reverse plus K2 plus K2 again, because K3 is going to cancel. So now we're going to use the last step, which is the one that ultimately produces our products, to be the rate determining step. And we'll give the rate law for that. So rate equals K3 times concentration of NO3, but we're going to substitute for K1F times N2O5 concentration over concentration of NO2 times K1R plus 2 K2s times concentration of NO. But concentration of NO is K2 over K3 times concentration of NO2. Concentration of NO2 cancels all out, and this just gives us some constant that's made up of K1 forward, K2, K1R, K2, K3, just some overall constant, times concentration of N2O5. And that matches the experimental rate law. And so this could be a mechanism for this reaction. I know that was pretty complicated. And the good news is the AP exam will never ask you to do anything this complicated. What they ask you to do is something more like the previous example that we did, where you just have to take a reversible reaction and make the forward and reverse rates equal to each other, and then use that to substitute for an intermediate, and then get rid of that intermediate in the slow step, which isn't really technically the steady state approximation, but AP calls it that.